Okay, so you have heard the first and the second ring for class. Now, questions. Last week we had started studying the magnetic field. Well, the one source of magnetic field was the rocks, naturally found magnets. And the other source that we had shown was the wires, currents. So if you have any current carrying wire, this creates a magnetic field. Now, we didn't stress it that much, but I mean, we had also said that, okay, if you have magnets, it has a north pole, south pole, then you can show the magnetic field as in terms of magnetic field lines, which go from the north to the south pole of a magnet. If you have a current carrying wire, the magnetic field lines will be, the direction of the field lines will just follow your right-hand rule. So just point your thumb in the direction of the current. So then your fingers, other fingers, just show the direction of the magnetic field lines. So in this case, the magnetic field lines start from the top and they go to the bottom. So if you look at it from the sides, the current is coming out of the screen. If this is the current coming towards you, so this is the thumb, the magnetic field lines are going counterclockwise. Then we looked at the force that the magnetic fields exert on currents, current carrying wires. And then we said that if we have an arbitrary wire, if you take some very small segment of this wire, so you have an arbitrary current carrying wire with a current I, then the force acting on this wire due to the magnetic field was given by the current multiplied by dl, the vector product with B. So you see, this is our vector dl. It is pointing in the direction of the current. The current is flowing in that direction, so that is the direction of dl. So this was the force acting on this segment. So in this example, if, let's say, the magnetic field is pointing out of the screen, if this is the direction of the magnetic field, at this point, what would be the direction of the force? Okay, so let me see the right hand. Fingers in the direction of dl, that is the first vector over here. And then you rotate your hand such that B points in the direction of the magnetic, your palm is in the direction of B. So this is the direction of the force. Downward, in this case. Any questions on how to use the right-hand rule to obtain the direction of the force? Any other questions? Now, today we will start studying the sources of magnetic fields. Now, one source of magnetic field is, as we had said before, the current. So if you take a straight wire, an infinite straight wire, carrying a current I, well, we had already said that in this case, the magnetic field lines have such a shape. They just encircle the wire. And the magnitude of that magnetic field is experimentally found to be proportional to the current and inversely proportional to the distance from the wire. So you see, at this point, the right-hand rule tells me that the magnetic field line is pointing out. So the magnetic field at that point is pointing out, and its magnitude is proportional to the current. If you double the current, the magnetic field over here is doubled. It is also inversely proportional to the distance from the wire. This R over here is this distance. And the proportionality constant is chosen to be mu 0 over 2 pi I over r. Now this here, just like the k or the epsilon 0 we had in the case of electrostatics, here we have another constant, mu 0. And mu 0 is defined as 4 pi times 10 to the power minus 7. What's the unit? Well, Tesla meter per ampere. You see, if you divide by distance, meters should just cancel. If you multiply by ampere, the ampere should cancel, and what should remain is Tesla. By the way, this is exact. It is exactly equal to that number. Because it's not measured, it's just defined. Mu 0 is just defined to have that value. It should be minus 7, no? Yes, it's minus 7. Now, let's do an example. Let's assume we have a wire. And then next to it, we have another wire. And they are both straight parallel wires. Let's just say that this wire carries a current I1 in upwards, and the other wire also carries a current. It's I2, and it's also upwards. Now let's see. This wire will create a magnetic field around it. And what will be, let's also call the distance between them d. What is the magnetic field that this creates at the position of this wire? What is the direction, first of all, at this point? Well, take your right hand, thumb in the direction of the current. Your fingers would point the direction of the magnetic field. So right here, it will be inside. What is the magnitude of B1? The magnetic field created by this wire. I over d, I1 over d. So this wire creates a magnetic field at the position of this wire. So this is a current carrying wire in the presence of a magnetic field, so it will feel a force. What will be, let's just take a very small segment. What will be the direction of the force that this segment will feel? Toward the left, right? Well, B is into the screen. dF would be just I dl cross B. dl is upward. My palm points in the direction of B, so it is in this direction. So that will be, this is the direction of the force. dF. So if we have two wires parallel to each other, and both carrying a current in the same direction, they will attract each other. And, well, let's just calculate it. What's the magnitude of this dF? I2 times B1 times dl. This will be the magnitude of the force. So the force per unit length, is just I2 times, well, we had already calculated B1. It will be mu 0 over 2 pi I1 over d. No, sorry, this is I2. Or the force per unit length is mu 0 over 2 pi I1 times I2 over d. What will be the direction of this, the force that this will feel? Let's study that. This will create a magnetic field at this point. What will be the direction of the magnetic field created by I2 at this point? The direction. Well, thumb, it's pointing outward. So this is, at this point, the magnetic field will be out, B2. So if we just take a dl over here, another very small segment of the first wire, what will be the direction of the force? Well, this is dl. B is pointing towards you. So this is my thumb. So the force will be in this direction. So both of them will feel an attractive force. Well, this is also consistent with Newton's third law. If wire 1 exerts a force on wire 2, then wire 2 should exert a force on wire 1 equal in magnitude, opposite in direction. So that's what we actually see. So if we change the direction of the currents, what will happen? Well, if this current is, let's say, moving downward, it wasn't moving upward, but moving downward, then it will create a magnetic field into the screen. And the corresponding force, dl cross b, will be outward, so they will push each other. So in a sense, if you have identical currents, they are attracting each other. If you have opposite currents, they will repel each other. Now let's say that we have the currents are carrying 1 ampere. And the distance is 1 meter. What will be the force per unit length? Now let's calculate. dF by dl. This will be equal to mu 0 is 4 pi times 10 to the power minus 7 Tesla meters per ampere. I1 and I2 is 1 ampere squared. Divided by d is 1 meter. And we also have 1 over 2 pi. Well, that 2 pi will cancel this 4 pi, leaving behind that 2. And so the force per unit length will be just 2 times 10 to the power minus 7 newtons. And in fact, this is the definition of ampere. This is how we define 1 ampere. You see, before we were talking about coulombs, but we didn't really define the coulomb. We said that one electron has the charge 1.6 times 10 to the power minus 19 coulombs. But what is 1 coulomb? And so in terms of coulomb, we define the ampere. But actually what we do is, this is how we define the ampere. So you just take two wires, make sure that they carry the same current. Well, the easiest way to do is you take one wire and you create such a system so that both wires are carrying the same current. They will push each other apart with some force. The force per unit length is equal to 2 times 10 to the power minus 7 Newton if their separation is 1 meter, then the current is just 1 ampere. This is how we define the ampere. So you just create the system, you send some current, measure the force per unit length, you change the current until you obtain the force per unit length to be 2 times 10 to the power minus 7 newtons. Once you reach that value, at that value you know that the current that you have is 1 ampere. So in this way, when I said mu0 is exactly equal to this value, that is just a definition of mu0. This is how we define that constant. In terms of that definition, we measure the ampere, 1 ampere. When you determine the current, the 1 ampere, there will be some uncertainties. Experimental uncertainties are over here. And then you have, once you have the ampere, 1 coulomb is just 1 ampere times second. So once you know the ampere, we know the coulomb. Well, let's do any questions on here, the force that the two wires exert on each other. Well, if there are more than one wire in your system, you can still calculate the magnetic field that they create. They say here there is a current out of the screen with a current I. Here the current is running into the screen with I. Let's see, midway, this is the point A. What is the magnetic field at the point A? At this point. Let's just also call this the whole distance to be L. What will be the magnetic field over there? Well, let's first calculate the magnetic field that each one creates. Let's start with this one. Take your right hand thumb in the direction of the current. So your fingers curl in the direction of the magnetic field. So in that case, just pointing up. So there is a magnetic field from this one. Let's call it B1. Well, if you look at the second current, well, the current is going into the screen. Use your right hand. So your fingers will point that the magnetic field is again pointing upward. Let's say this distance is L over 2. This distance is also L over 2. So B1 and B2, they are both equal. And their magnitudes is, we had already determined their direction. So what are their magnitudes? It will be mu0 over 2 pi I over L over 2. So the total magnetic field at the point A will be just B1 plus B2, which is mu0 over 2 pi times 4I over L. Let me also use some axis. This is x, y, so it's in the j hat direction. That's the direction of the magnetic field. Well, let me choose another point over here, somewhere over there. At a distance, well, let's also call that L. Now what will be the magnetic field over there? Okay, again we will have to calculate the magnetic field created by this current and the magnetic field created by the other current and just sum them vectorially. From the first current, what will be the direction of the magnetic field created by this current? Well, make your right hand thumb in the direction of the current, so it's pointing somewhere like this. That is 90 degrees with respect to this line. That will be the direction of P1. In the case of this current, well, it will be pointing in this direction, again 90 degrees with this line. What is this angle? No, this angle, sorry. Well, you see, this is 30. This is 60. It's a bad equilateral triangle, but you see, here I have an equilateral triangle, right? This line, this vertical line, divides this angle into 30 here and 30 over there. But this is perpendicular to this line. 30 is over here. I have 60 on the other side, so that angle is 60. And similarly, this angle over here will also be 60. Because you see, these lines are perpendicular. Here, I already have, with this line, I have 30 degrees, so that is also 60. Yes? No. It's just my drawing sucks. So let me draw it again. So here I have one current. Here there is the other current. So this is supposed to be a right triangle. No, not a right triangle, but isosceles triangle. B1 is this one. B2 is this one. This is a right angle. And this is a right angle. So you see, this is 60, this is 60, this is 30, this is 30. Okay, now this is a better figure. So you see, this red line makes 90 degrees with this one. So already 60 is over here, so this is also 30. And similarly, this is also 30. This is 30 because this is a 90 degrees angle. This is 30 because this is a 90 degrees angle. In this figure over here, you see this angle itself is 30 degrees. Okay, now let's come back over here. Now, when I sum these two, they will in fact coincide with this line, because they have the equal magnitudes. B1 prime is equal to B2 prime. They are created by the same current, by occurrence of same magnitude, I, and their distance is the same. So their magnitudes are both mu0 over 2 pi I over L. Now, when I sum these two up, I will in fact get this vector over here. I will get this vector. And in fact, the magnitude of that vector, so B at the point C is B1 prime plus B2 prime, which will be equal to mu0 over 2 pi I over L, and again in the j direction. These two vectors are vectors of equal magnitude, and if I just carry this over here, this angle is also 60 degrees. So here I have an isosceles triangle. This length is equal to this length, it's equal to that length. Oh, sorry, there's no magnitude. So the total vector is the sum of these two vectors, and it is given by this.
Can you explain the direction of magnetic field?
You mean B1, B2, or the total?
No, B1.
Well, how do you calculate the direction? Thumb, your right hand, if we start from I, your thumb in the direction of the current, your fingers will curl in the direction of the magnetic field. And so basically, here the magnetic field lines are circling this current I. It's always perpendicular to the radial vector. So at this point, this is my radial vector connecting the current to this point. The magnetic field line is going in this direction. So the magnetic field is tangent to that, and it is 90 degrees with this line. And similarly over here, since the current is into the screen, the magnetic field lines will be going clockwise around this current. And at this point, it's pointing in this direction, in the clockwise sense. And it is perpendicular to this line.
I have a question regarding mu0 and it being divided by 2 pi. If mu0 is a constant number and we're dividing it by another constant number, why not just define mu0 as 2 pi times 10 16?
Why do we keep, let's go back. Why do we keep the 2 pi over here and multiply here with 4 pi? Well, what does 2 pi r remind you? It's the length of the circle. Okay, so let's take a circle. Let's assume we have a current coming towards you. Let me take a circle around it. This is an imaginary circle, not a real one. It doesn't exist. Let's say that circle has a radius r. Now the magnetic field on that circle, its magnitude will be mu0 I over 2 pi r. Well, let me multiply B with 2 pi r. This is mu0 times I. Well, the nice thing about this one will be, in a moment, you see the right-hand side doesn't depend on r. no matter how large a circle you take, if you multiply b with the circumference of that circle, you get a constant, no matter how large you take your circle to be. Well, let me try to change it slightly. This is b times, let me write it this way. Now what I'm doing is, I'm imagining this circle to be made up of very small segments. Now it covers all my circle. Each one of these has a length dl. So mu0 times I is equal to b times the integral of the length of these segments, or the sum of the length of those segments. Well, let me take one more step. B times dl. B is constant. The magnitude of B is the same around my circle. So I can just move that B into the integral. Well, now let's see. I have a vector dl whose magnitude is this number. Now at this point I have another vector, the magnetic field vector, whose magnitude is this number. And at this point, on this segment, B and dl, they are pointing in the same direction. So if I take the scalar product of these two vectors pointing in the same direction, their scalar product is just the product of the magnitudes. So this b dot dl, this product of the magnitudes, is nothing but the scalar product of those two vectors. So now we have this one, b dot dl is equal to mu0 times I. And here there are no factors of pi. Now, of course, for this expression, we use a special form of the loop. We assume the circle. Furthermore, we assume the special wire. It's an infinite straight wire. But it turns out that this relation is true for every wire, for every loop. So whatever wire you have, you don't even need to have a single wire. You can have, I don't know, hundreds of wires that you like. This relation is still valid. Well, let me just change it slightly. This is the integral of the magnetic field around any closed loop will always be equal to mu0 times the total current running through the area bounded by the loop. And not to have any factors of pi over here, we just put the pi's over there in mu0 and then divide by 2 pi. Now this will be the analog of Gauss's law in magnetics. You see, in Gauss's law, in electrostatics, we use the Gauss's law to calculate the electric field for quite symmetrical charge configurations. Here we will use this law, the Ampere's law, to calculate the magnetic field of very symmetric current configurations. Well, there are a couple of things that we have to pay attention to. Let's see, let's assume that we have a loop. We have such a loop. It is an arbitrary shape. Let's say here we have there is a current running I1 out of the screen over here. And there is another current over here going into the screen. There is a third current outside the loop, out of the screen. And a fourth current over here in that direction. Now let's apply the Ampere's law. Let's try to apply it. B dot dl around the closed loop. Well, you see, the first question we have to answer is, in which sense are we moving around the loop? Are we going clockwise or are we going counterclockwise? That's completely up to us. We can choose it, whichever way you like. So do you prefer clockwise or counterclockwise? Clockwise. Okay, let's go clockwise. So this is the direction of my loop. So I will be going clockwise. Now again, let's use your right hand. Your fingers in the direction of the loop. This loop. Your thumb points into the screen. That is the positive current. You see, this is a positive current because it's going into the screen. This is a negative current because it's moving in the opposite direction. So that is actually minus I1. So if you evaluate B dot dl around this loop, it will be mu0. Well, the enclosed current is plus I2 and minus I1. You see, I3 changes the magnetic field. B depends on I3, but that integral is independent of I3, just like in the Gauss's law. If you remember, in the Gauss's law, we said that if you assume any closed surface, the electric field at a given point on that surface will have contributions from charges outside the surface, but you integrate the electric field over all the closed surface, only the charges inside that surface contributes. Just like over here, I3 and I4 do contribute to the electric field along this loop. But when we sum them all up, their contribution of I3 and contribution of I4, they cancel. And the integral only depends on the currents inside the loop. That is I1 and I2. And just like we could have positive charges and negative charges, here we can have positive currents and negative currents. And to determine the direction of these currents, what we need to do is, again, use your right hand. Once you choose the direction of going around the loop, you assume you wanted to go around the loop clockwise, then the positive currents, your right hand tells you that the positive current goes into the screen and negative current comes out of the screen. They are pointing in opposite directions. So that's why this is minus, this is plus, consistent with my choice of the direction of the loop. If you had chosen the loop to be counterclockwise, in this sense, then this would have been a positive current and this would have been a negative current. But that doesn't change that relation in the sense that if you change the direction of dl, the integral also gets a minus sign. All of these gets a minus sign. So this relation still holds. This Ampere's law in this form is always valid, independent of how you go around your closed loop. The only thing you have to pay attention to is, as you are going around the loop, you have to be consistent with your definition of positive current and negative current. Once you choose the direction of the loop, the current going from one side of the loop to the other side will be positive, and if it's going in the other way, it will be negative. Just pay attention. Now, any questions?
Hocam, I3 ile I4 nasıl
I3 and I4. Well, let's see. The B will have contributions from current I1, from current I2, from current I3, and from current I4. The total magnetic field will be the sum of all these. Now, B1 dot dl around our loop will be minus mu 0 I1, because, or let me write it, mu 0 times minus I1. Because if there was only the I1, the magnetic field would be B1, and my Ampere's law, this is my Ampere's law, so I have the loop. Around the loop contains my current I1, so this is what my Ampere's law tells me. Now let's look at B3. This is the magnetic integral of the magnetic field created by I3. Well, let's see. What are the directions of the magnetic field lines created by I3? Do they go clockwise or counterclockwise? Well, your thumb, it goes counterclockwise. So the magnetic field lines created by I3 will look like this. Right? Now let's see. There is a segment over here, dl, pointing in that direction. So I'm going around this red loop in the clockwise sense. So how I calculate it, divide it into very small segments, and calculate b dot dl for each one of those segments and sum them up. So here there is a segment. It's pointing in this direction. The magnetic field is also pointing in that direction. So b dot dl is positive here. Well, let me move over here. Here dl is pointing in this direction now, but b is still pointing in that direction. So the contribution from this small segment will be negative. When I sum the positive contributions with the negative contributions, they just cancel. You see, in fact, if you just well, let me just explain that. That's a great comment. You see, the B's are different. Let me just imagine a very small segment. Well, let me take a very small angle. Here there is a dl. On the other side, this is my dl. B is smaller over here. You are right, B is smaller because I'm at a larger distance. How small? Well, it's inversely proportional to my distance. But now, this dl is larger than this dl. How much larger? Well, this dl is proportional to the distance. So when I multiply b and dl, here b is small, dl is large. Here b is large, dl is small. But when I multiply them, they are the same, but opposite in sign. So the contribution from this one plus the contribution from that one, it just gives me exactly 0 because of this 1/r dependence. You see, in fact, exactly the same phenomena happens in Gauss's law. Electric field decreases with the distance squared, but the area increases with distance squared. So it's just electric field times the area. Here, the magnetic field decreases with length, with distance. The length increases with distance, so it's the magnetic field times the distance, which doesn't change. Now, if you look at I1, Well, the magnetic field created by I1 is in that direction over here, but it is in the opposite direction over here. Here, dl is pointing in that direction upward. Here, dl is pointing downward. So both contributions add for a current inside my loop. But for a current outside my loop, magnetic fields here and here, they are in the same direction, whereas dl is pointing in opposite direction. So one contributes positive, the other contributes negative, the sum is 0. So the integral of B3, the contribution to the magnetic field due to the third loop around that, the red loop, will be exactly equal to 0. So that is why when we integrate B around that loop, there is no contribution from I3. And similarly, there won't be any contribution from I4. Any questions? Also keep in mind that it's also not important what is the direction of that current, in the sense that, let's say, here I have a loop, my hypothetical loop. One current just comes here from below the loop. It goes in that direction. Another current can come here. And then goes below the loop. Let's say this is I1. This is I2. Let's even imagine a third one. Okay, this is I2, I3. They are not parallel, not perpendicular to the screen, not into the screen, but it doesn't matter. B dot dl okay, first thing, in which direction should we go around our loop, clockwise or counterclockwise? Counterclockwise, let's go in this sense. Not I, dl. What is the direction of positive current? Positive current is out of the screen, or from below to above. Negative current is from above to below. So let's see, B dot dl is mu 0. Times, well, I3, is it a positive current or negative current? Well, why? Because it comes somewhere over here, it enters the area and continues like this. So it is the negative current, because we said the positive current is in this direction. So it's minus I3. What about I1? Well, it comes from behind the screen and comes to the front of the screen, plus I1. What about I2? Well, it again comes from below the screen, so it kind of goes like this. This is how the I2 goes. So it's again positive. Now let's do an example, or well, let's give a break before the example. Any last questions? Okay, see you after 10 minutes.